Welcome to another video in the series Electronics, the Story of One Human Lifetime by David Beams and Gary James. I am your narrator today. I am David Beams, Associate Professor Emeritus of Electrical Engineering. And the subject of this video is the announcement of the availability of resources for amplifier circuits. These are resources that I developed during my teaching career. The resources that I'm going to be mentioning today are not the entirety of those that I've developed. There will be more that will be made available in the future, and I will post announcements when that happens. In this first group of materials for amplifier circuits, let me show you what is being made available. Under tutorials and notes, there are my notes on the Miller effect, my notes on MOS differential pairs with active loads, a derivation of the output currents in a BJT differential pair using a current mirror load. There is an analysis of a non-inverting amplifier circuit that uses a current feedback operational amplifier. And there is a derivation for computing the common mode input voltage range of a two-stage CMOS op-amp. Under Excel spreadsheets for design and analysis, we have an analysis of the two-stage CMOS operational amplifier. I have a spreadsheet for calculation of MOSFET internal capacitances for high-frequency simulation of amplifier circuits. And I have a spreadsheet for calculating the bandwidth of an amplifier that's composed of cascaded stages using operational amplifiers. Under LTSpice circuits, to begin with, I have only one. This is the two-stage CMOS operational amplifier. Let me describe a couple of these things in further detail. Here is the LTSpice two-stage CMOS operational amplifier. It's very similar to a circuit that is described and discussed extensively in the Cedra and Smith text on microelectronic circuits. If we look at the functional blocks of this circuit, we have bias circuits or current generators. We have a PMOS differential pair with a current mirror load. These two together form the first stage of this two-stage op-amp. And the second stage is this common source amplifier with an active load. That is the output stage of the op-amp. And I've overlapped the rectangles of the bias circuits and the common source amplifier to emphasize that MOSFET M3 here is part of the bias circuits, but it is also the load of the common source amplifier. Now, we also have two sets of model parameters for NMOS devices and PMOS devices. One set of parameters comes from the Cedra and Smith text, and the other comes from Razavi's text on analog CMOS design. And by changing the names of the models involved in the circuit, you can change the model parameters from one set to the other and see what effects that may have. Now, one other thing I want to point out, these three components, they are not part of the op-amp. They serve various purposes. Let me explain here. You'll notice that there is a 1 megohm resistor from the output tied back to what is the inverting input. And resistor R3 I've currently set from the inverting input to ground is currently set to 1 gigohm, essentially an open circuit. The point of this resistor is that the op-amp, when you go to do an analysis, the first thing LTSpice will do is determine the DC operating point. The inverting input will be at the same potential as the output of the op-amp. And so we'll find the proper DC operating point for all the op-amps in the model. Now let's take a look here, however, at capacitor C2. You notice that it's 1. That's 1 farad, not 1 microfarad. It is 1 farad. That's a huge capacitor. And together with resistor R2 from the output back to the inverting input, it forms a low-pass filter with a ridiculously low cutoff frequency. Essentially, for AC purposes, the inverting input is held at ground. Why do we do that? Well, on the non-inverting input, we have an AC voltage source with an amplitude of 1 volt. And then with the inverting input held at ground, AC ground potential, the voltage, the AC voltage that's developed at the output is numerically equal to the open loop gain of the op amp. Now, if you want to do an analysis involving this op amp with a real application circuit, you can remove C2, or you could set it to 1 femtofarad, 1,000th of a picofarad, essentially 0, but set it, change the 1 to 1F, and then you can change the values of resistors R2 and R3 to the realistic values that would be applicable to your application, and you can run your analyses. Using the circuit as you see it, here is a plot of the open loop gain of the 2-stage CMOS op amp versus frequency from, let's see, 1 hertz to 10 gigahertz. The DC open loop gain is about 65 decibels. And it, just as a quick estimate, eyeballing it, somewhere around 30 kilohertz where the gain drops. The open loop gain drops by about 3 dB. Okay. The second resource I want to talk about briefly is the spreadsheet for analyzing the 2-stage CMOS op amp. Here is the schematic diagram being analyzed, and here are the here are the calculations of the spreadsheet. The cells that represent user entered values are in this light tan color. And here we have the supply voltages, the threshold voltages of the NMOS and PMOS devices, channel length modulation parameters, width to length ratios of all the devices. We have electron and hole mobilities. We have oxide thickness and channel length. And we have the reference current that sets the operating point of the bias circuits. And the last thing that you enter is this compensation capacitor, which is used for dominant pole compensation of the op amp. And the op amp, or the spreadsheet, produces a number of calculated results, including the voltage gain of the differential pair with its active current mirror load. That's the gain of the first stage. It calculates the minimum and maximum common mode input voltages for the op amp. And it calculates the gain of the common source amplifier, the second stage, and also computes the gain both in volts per volt and in decibels of the overall operational amplifier. And it computes the minus 3 dB frequency, the break frequency of the open loop gain. Now, one other thing it computes is a resistor that you could replace the reference current source with and achieve that reference current. So in this case, something like about a 15K resistance, replacing that current source should draw the same reference current, which at the moment is set to 500 microamperes. Now, there's one difference between this 2-stage op amp and the LTSpice model. In the schematic of the LTSpice device, these 2 transistors in the differential pair, their substrates are tied to the positive supply rail. So the body effect will come into play in the calculations of the LTSpice model. Here, to simplify the analysis, the substrates are connected to the sources, so there is no source to substrate voltage difference, and the body effect does not come into play. let's put the wraps on this. Remember, the link is in the video description. And if you find these resources useful, intriguing, helpful, beneficial, whatever, leave a comment, let us know. So we appreciate your visiting with us. Keep those cards and letters coming. I am David Beams, and it has been my privilege to be your presenter today, and I will see you again soon in another video in the One Human Lifetime series.